This section we get introduced to the lovely world of chords. But sadly for some of you, we aren't talking about music. In geometry, a chord is a line segment whose endpoints lie in a circle. Like this guy here, a lovely line segment with endpoints on the edge of our circle. Every time you have a chord, there is a section of arc that gets cut off, as if the chord is a cut line for something that has sliced through our circle. That chord is known as its related arc. For this chord here, this blue arc is the related arc. That chord and that arc are linked together. We're going to be coming back to that a lot. Now think about this. Does a diameter count as a chord? What do you think? It does count. A diameter is a chord. It's just a special case. A diameter is a chord that goes to the center of the circle. We now come across a phrase that will come up a ton in the theorems in this section, within a circle or in congruent circles. So you need to get down why that phrase even exists and what it entails. First, the within a circle part. Let's say I have a circle, and on this circle there are two 90-degree arcs. I can say for sure that the 90-degree arcs are congruent. They are exactly the same size and shape. It isn't just because of the 90 degrees though. This is another 90-degree arc, but in another smaller circle. This blue 90-degree arc is smaller than the red arcs. It isn't enough that they are both 90 degrees. But these two red arcs are congruent. They're within the same circle, so they must be the same size. Now let's look at the or in congruent circles part of the phrase. Here I have a pair of congruent circles, since their radii are the same size. The circles both have blue 130-degree arcs highlighted on them. Those 130-degree arcs are congruent too, because not only are they 130 degrees, but they are also in circles that are the same size. Since the circles are the same size, taking a 130-degree chunk out of both of them results in pieces of the same size. That's where this phrase, within a circle or in congruent circles, comes from. The next huge batch of theorems all work whenever you're either within the same circle or in congruent circles. One or the other. You will get sick of seeing this phrase by the end of this lesson. In section 10.6, when arcs were first introduced, we said that the measure of an arc was equal to the measure of its central angle. Earlier we dealt with chords for the first time, and it said that chords cut off a chunk of arc. I said that the chords and the arc they cut off are also linked. So we have arcs and central angles linked together, and the chords and arcs are linked together. So in fact, they're all linked together. A chord, its arc, and the central angle associated with it are all one big, happy, linked, inseparable, related family. That fact leads us to the next 6. Yes, I said 6. Theorems and converses. Good Lord, look at all of those. I told you that phrase within a circle or in congruent circles came up a lot. I didn't want to inundate you, but I also didn't want this video dragging on for 3 hours. Plus, if you look closely, these are all very similar theorems. In fact, I can summarize them all with a picture on the next slide. Some of you will undoubtedly pause here and write all these down, but here's the basic summary. I told you that these 3 things are all linked together. The chords, its arc, and its central angle, all intimately related to each other. Let's make a duplicate circle to work with. This would work just as well if I illustrated this in a single circle, but I think this is clearer. For the record, these circles are both congruent, so the 6 theorems from before all work. Remember, within the circle or in congruent circles. Here are the congruent circles. All 6 of these theorems boil down to this. If you have the same circle or congruent circles, and you know if any one of those 3 things are congruent, then you know the other 2 are congruent also. For example, if you know you have 2 congruent central angles in congruent circles like this, then you know that the chords are also congruent and the arcs are also congruent. This is the first time you have seen this, but you can also mark arcs congruent with tick marks, just like you do with line segments. Similarly, if you start out knowing that 2 chords are congruent in congruent circles, that's enough to know that the central angles are also congruent and the arcs are also congruent. See, this isn't too bad. Finally, if you start out knowing that the 2 arcs are congruent, that's enough to know that the central angles are also congruent and that the chords are also congruent. That is the basic crux of all 6 of those theorems from the previous slide. If you know one piece of this linked family is congruent, then all family pairs are congruent. So much better than memorizing 6 similar theorems, right? Here I have a blue chord. What happens if I move this chord away from the center of the circle? What is happening to it? It should be readily apparent, but the farther away from the center it gets, the smaller it has to be in order to stay a chord. With that in mind, what do you suppose you could say if you had 2 chords that are the same size? Since chords get smaller the farther away you get from the center, if 2 chords are the same size, then they have moved the same distance away from the center of a circle. That brings us to these 2. They put into theorem form that concept I just did. If chords are equidistant from the center, they have shrunk the same amount, so they must be congruent, or the converse. Incidentally, you are going to need to get used to this construction here. This is one way to show chords are equidistant from the center. The red line segments might also have had tick marks instead of the length of the value. either way, but the perpendicular is important as the shortest distance between a point, the center, and a line, the chord, is the perpendicular line. If on a problem you see a construction that looks similar to this, then they are probably showing you equidistant from the center, and they are referencing this theorem or its converse. Let's get back to this picture with our interconnected related family. What I want to do now is draw in the diameter to the chord that is perpendicular to it. This one here. What do you suppose that diameter does to our family there? What happens to the chord, the arc, and the central angle? If you said that diameter bisects all of them, you win a prize! 500 brownie points! What are brownie points worth? Nothing. But you have 500 of them. Be proud. This theorem is that idea. Sometimes people ask, and this theorem does work just as fine with a radius too. In fact, I wish it had said radius instead of diameter, but I will suffer through. Radius or diameter, it doesn't matter. If it is perpendicular to the chord, then it is bisecting them all. The theorem also doesn't mention the central angle, but it does get bisected too. They are all linked. Now, where have I heard that before? There is this theorem too, which is almost the converse. Now, instead of starting with the radius or diameter perpendicular and concluding it bisects, this time you start with the fact that it bisects, and thus you can conclude it's perpendicular. I should note here that once again, all of these things are linked. The theorem says that you start with the chord bisected, and that is how you will most often see it in problems, but it actually works for any of them. If the arc or central angle is bisected, then you know it's perpendicular to the chord too. There's that linkage thing again. This last theorem is just like the last two and follows from them. I won't say too much about them, but it is an interesting nugget. In a circle, the perpendicular bisector of a chord goes through the center of the circle. Here's the perpendicular bisector that we have been working with, and it does indeed go through the center. No matter how you draw your chord, the perpendicular bisector of that chord must go through the center. And that's the last of the 11 theorems from this section. That's a lot, but many of them are very similar. And none of them are too hard, just a lot to keep straight. It helps a lot to remember that a chord, its arc, and its central angle are all linked together so strongly.